Welcome back to Science 10. So you should have finished the angle of incidence and rate of temperature change lab, in which we adjusted the angle and determined what how that affected insolation, or the amount of energy reaching the Earth's surface changed. Okay, so on the next page here, we'll look at this. The Earth's shape and angle of incidence plays a large role in creating the Earth's climate. From the equator to the pole, there is a progressive decrease in insolation year-round. And that's as we saw from this lab here. As a result, the average annual air temperature is the highest at the equator and decreases as you move towards the poles. There is little variation in the number of hours of daylight with the seasons at the equator, but the number of hours of daylight varies progressively with the seasons at increasingly higher and lower latitudes. There is therefore more variation in average daily temperature throughout the year as you move closer to the poles. Okay, so if we look over here, Arctic Bay, Canada, so as you can see, as the seasons change, the average daily temperature changes drastically. So over here in the summer, June, July, we're sitting at around 8 degrees C, but November, December, January, February, we're at -30. Whereas near the equator, it's consistently warm, so 28, 26 degrees C approximately throughout the entire year. Okay. There are other things, though, that happen here. Absorption and reflection by the biosphere. As soon as the radiation from the sun reaches the Earth's outer atmosphere, it may be reflected or absorbed by particles of matter. When particles reflect energy, they simply change the ray's direction. So particles floating in the air, they could reflect incoming sun radiation, or of course they could absorb the energy. The energy is converted into another form of energy called kinetic energy when they're absorbed. And the word kinetic means moving. So moving energy, when a substance absorbs energy, the temperature of that substance goes up because its kinetic energy is increasing. And temperature is a measure of this moving energy that substances have. So absorption and reflection of solar radiation occurs in all three components of the biosphere, so that region where we live, looking up into our atmosphere. The reflected radiation either goes back into space or is absorbed elsewhere in the biosphere. Some of the absorbed solar energy is re-emitted as thermal energy, which warms the atmosphere, lithosphere, and hydrosphere, so that region above us. Some of that kinetic energy resulting from the energy absorbed is used to drive the movement of water through the hydrologic cycle, so it gives us enough energy to cause water evaporation and collecting in clouds and then falling back again. And also the movement of air in terms of wind. A small amount of solar energy is converted into chemical energy through photosynthesis, as we've seen earlier, and is then passed on to other organisms. So some of that energy is used as photosynthesis in plants, and of course we saw what happens with that. The layers of the atmosphere, the troposphere, stratosphere, mesosphere, and thermosphere, contain different mixtures of gases. These different gas mixtures absorb or reflect the energy from different areas of the electromagnetic spectrum. High energy radiation such as X-rays and gamma rays are absorbed by oxygen and nitrogen gases, mostly in the mesosphere, thermosphere, and stratosphere. Ozone absorbs most UV radiation, ultraviolet. Carbon dioxide and water vapor in the atmosphere absorb infrared radiation, as do other gases such as methane. Visible light and radio waves make it to the Earth's surface with very little absorption of the atmosphere. So you can see different types of radiation, such as that we've seen back here in terms of the electromagnetic spectrum. Different amounts of energies are absorbed by specific gases in the atmosphere. Radio waves go right on through, but some of these other ones are absorbed by different types of gases. Okay, keep on going here. Cloud cover and atmospheric dust. Most clouds and atmospheric dust particles less than 0.66 millimeters in diameter are found in the troposphere. The amount of cloud cover and atmospheric dust over any region varies daily, but some regions will have more cloudy skies, and some regions usually have relatively high levels of atmospheric dust. Human activities also caused an overall increase in the atmospheric dust in some regions, especially over those industrialized nations. So, for example, Los Angeles has a lot of dust sitting over it. And what happens here, as I illustrate here, cloud cover or dust can act as a blanket. So what does that do? Clouds reflect some incoming solar radiation back into space. So if we imagine this sitting over here, radiation coming from space, it's reflected back away from the clouds. So as a result, the air temperature could be cooler on a cloudy day. However, clouds also absorb energy that is emitted by the Earth's surface, which help keep the planet warm. So it reflects incoming radiation, radiation that's given off by the Earth, such as the thermal energy of the Earth, releases, reflected right back. Just like how a blanket keeps you warm at night, it reflects back your energy towards you and keeps you warm, so it doesn't escape. It does the same type of thing here. Atmospheric dust behaves in a similar way. It can shade the Earth's surface from incoming radiation, reducing the amount of solar energy that reaches the lithosphere and hydrosphere. Atmospheric dust also absorbs some of the incoming energy from the sun and some thermal energy emitted by the Earth's surface. When a natural or human-made event such as a volcanic eruption or a forest fire expels large volumes of dust, the effect on climate can be significant and often quite difficult to predict. Next, albedo, a reflection by the lithosphere and hydrosphere. The solar radiation that reaches the Earth's surface is either reflected or absorbed, as we've illustrated here on the previous page. The amount of solar energy that is reflected versus the amount absorbed depends upon also the type of surface that it's hitting. So the radiation hitting the Earth, it depends on this versus this. The same region, but as you can see, different seasons, summer versus winter, that will affect how much radiation is absorbed by the Earth itself. The albedo of a surface is the percent of solar radiation that is reflected. So, of course, you likely are aware that light-colored, shiny surfaces such as snow reflect more energy than darker, duller surfaces such as a forest or soil. And you don't have to think too far. If you think of a hot summer day, touching a white or lightly colored car versus a black or darker car, the darker colored car would feel hotter to the touch because it has absorbed a lot of solar radiation and its temperature is increased, versus a lighter silver or white car, it reflects energy so it doesn't heat up to the extent of a darker colored car. And look at this, the same thing holds true here. Snow cover, it's light color, it'll reflect a lot of radiation and not get heated up as much as a region like this, which is darker, it absorbs more energy, and as a result becomes warmer to the touch. So for example, the albedo of the polar ice caps is much higher than the albedo of the forests of northern Alberta. So again, albedo is what percent is reflected. So the more reflection, the lighter colored the surface, the larger the albedo number. So 30% versus 0.3%. And of course, deserts in Africa, they're lighter colored too, and they would reflect a lot as well versus darker soil. Most areas in Canada have a higher albedo in winter than in summer, obviously, as we can see here, due to the change in amount of snow cover. Figure D12 shows the albedo of the Earth's surface according to the data collected from April 7th to 22 on 2002 by satellites. The highest albedo numbers are red, so you can see the northern regions are red because snow cover, reflecting. Also here though, Africa, that's interesting, but you can look at it as, oh, it's the Sahara Desert. Sahara Desert is also a light color, so it reflects a lot of the incoming solar radiation as well. Yellow and green show regions with intermediate albedo values, and regions with low albedo values are blue or violet, etc. Okay? So snow and desert regions will reflect a lot of incoming radiations, but of course this desert is near the equator, so it's also receiving more radiation too than up here. So even though it reflects a lot, it's going to absorb a lot too because of where it is on the planet. All right, we'll keep on going to here. Look at the natural greenhouse effect, and that'll lead us to the greenhouse lab that we're going to be doing. Natural greenhouse effect, some of the radiant energy that is absorbed by the Earth's surface is re-emitted into the atmosphere as infrared radiation, which has high thermal energy. This re-emitted thermal energy keeps the temperature of our planet range in a region that supports life. Most of the thermal energy is absorbed in the atmosphere by clouds, water vapor, and such gases as carbon dioxide and methane. Without the atmosphere, the thermal energy would just simply escape to Earth, and the Earth would be cooler. So again, those gases act like a blanket, keeping that energy in close to the Earth, keeping us warm. The absorption of thermal energy by the atmosphere is known as the natural greenhouse effect. Without the natural greenhouse effect, the average temperature of the Earth would be about 33 degrees lower. Greenhouse gases are gases that contribute to the greenhouse effect, so those gases that help absorb energy and keep the energy in towards the Earth. Since it is present in such high amounts in the atmosphere, the main contributor to the natural greenhouse effect is water vapor. However, carbon dioxide and other gases, methane and nitrous oxide, which is also dinitrogen monoxide, also absorb significant amounts of thermal energy. So as we can see, solar energy comes in, heats up the planet. Of course, energy escapes from the Earth as well, but those gases keep it in here. So we can see infrared radiation is absorbed by the atmosphere and keeps this region the same temperature. And of course, some escapes, but a lot is reabsorbed. Lastly here, net radiation budget. We'll look at that next time, folks. So that's basically what the natural greenhouse effect is. If we look at our question sheet where we're at, back here, you're supposed to do questions 1 to 3, and now you should be in a spot where you can do questions 4 to 10, I believe. So we talk about reflection, absorption. There's some questions here involving albedo, and then up to number 10, the greenhouse effect, and then number 11 is the next section. So you should be able to do questions 4 to 10 at this point. All right, we'll see you again.